Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 12. We were talking last time about equilibrium phase diagram, particularly in context of iron carbon equilibrium diagram, and saw the various important transformations like the eutectic, the eutectoid, the peritectic transformation which was taking place in context of the change in phase of iron into two phase or single phase, so on and so forth. So we also discussed about the utility of the point at temperature 723 degrees Celsius, which is concerned with heat treating the material to have different strengths or different hardnesses within the material. So it is of extremely high engineering relevance, and in context of that we are going to discuss today the control of material properties, which are very important for metals and even alloys, which have to be used for different engineering applications where the requirement of the hardness or the requirement of strengths are varied in nature. So the material properties of metals and alloys can be controlled by various methods to make the material suitable for a given application. For example, one of them is just alloying, where you are using some trace amount of materials, each of which would create some kind of a difference in the crystal structure by either pre-hardening it or doing something related to the regularity of the lattice structure of the metal, where enhanced properties can be felt coming out. Heat treatment, where you can rapidly heat and cool, and this can also result in quite a bit of changes in the structure, the crystal structure of the material, which can lead to the various changes in the material properties. And then obviously the mechanical working and recrystallization, which is another way in which strain hardening can be induced, and then the temperature can be taken just to above the recrystallization temperature, so that it can start afresh and be able to harden to an extent that you want it to be hardened. So think of it that in a manufacturing process, when we are talking about a primary or a secondary process and we want a desired property, like for example desired ultimate yield strength or desired hardness on the surface of a material, you not only need to worry about the primary or the secondary manufacturing processes, but also the after effect of putting the material coming out of these processes into use, engineering use. So for example, in an assembly of different linkages, where each of this link has been formulated through a manufacturing process, if enough amount of surface hardness or if amount of surface stability is not there, or in fact if there is low ultimate yield strength of the material, the linkage may completely fail. Okay. So then that is the reason why these heat treatment processes become very, very important from the aspect of manufacturing. So the first process, alloying, obviously concerns the way that alloying of steels happen mostly. So let us say in the alloy steels, they are broadly classified into two categories. One is called a low alloy steel and another is a high alloy steel. So in the low alloy steels, the total content of the alloying elements such as chromium, nickel, molybdenum, vanadium and magnesium is kept within 5%, and each alloy element imparts a specific property to the original material. I have just tried to ensemble some of the properties which would be induced by these different, like aluminum tries to promote deoxidation, promotes nitriding, restricts grain growth. Typically a low percentage is something which is desirable. The material boron, for example, increases hardenability, typical percentage 0.001 to 0.003%, and used in steel with carbon content less than 0.6% often, which gives the effect of increased hardenability. You have cobalt, which can impair impact strength, impair the impact strength slightly, or it contributes to the red hardness or sustains hardness during tempering. You have chromium, which increases hardenability, again increases resistance to corrosion, abrasion and wear, increases high temperature strength. Typical percentages which we need of these chromium material is between 0.5 to 2 to increase the hardenability, and 4 to 8 to increase the corrosion and wear resistance. So it is a very important material from corrosion aspect. Okay. Then the material copper, which can increase corrosion resistant, again typically the percentage that is needed is 0.1 to 0.4%. So these are some of the materials which can actually impart desirable properties or effects by alloying into the basic crystal structure of iron. So you have a variety of other materials in the same manner. For example, what manganese does is to sort of counteract the brittleness from sulfur which otherwise gets generated into the mold, because sulfur is something that you have to get rid of, because otherwise it generates a lot of undesirable properties related to brittleness etc. of the casting. So typical percentage is about 0.25 to 0.40% to counteract the brittleness from sulfur. Similarly, manganese can increase hardenability, increase resistance, reduce the ductility and weldability, increase hardenability significantly, percentage again greater than 1 to increase the hardenability. Molybdenum, for example, increases strength, toughness, red hardness and hot strength when used with chromium, manganese and vanadium all in total. So the typical percentage here that you are looking at is 0.2 to 5%. In fact, molybdenum is used a lot in high speed cutting tools, particularly high speed steels. It is used in forged crankshafts, turbine rotors, high pressure cylinders, boiler plates, gears, so on and so forth. Similarly, nickel would increase toughness and impact strength, improve the corrosion resistance. These are some of the typical percentage ranges: 2 to 5% to increase the toughness strength, 12 to 20% to increase the corrosion resistance, and mostly nickel would be used in the case of hardened parts such as, let us say, high speed gears, ball bearings, so on and so forth. Then phosphorus, which is again used for increasing hardenability, machinability, increasing strength in low carbon steels and improving the overall corrosion resistance. So that is another aspect of the material phosphorus. Okay, so these are the various effects of alloying the elements on steel. Similarly, you can say silicon acts as a deoxidizer or improves magnetic properties when present in large percentages, or sulfur, which improves machinability of low carbon steels, but it creates a lot of brittleness within the structure, which is one of the reasons you want to get rid of the sulfur mostly in castings etc. Titanium, which increases the austenitic hardenability and reduces the martensitic hardness in chromium steels. Again, vanadium, which increases strength while retaining ductility, produces fine grain size, increases hardenability, and tungsten, which imparts again hardness and wear resistant and significantly improves red hardness and imparts strength at high temperature. So these are some of the consolidated effects of alloying steels by the various trace elements, and the percentages that you are seeing here are mostly very trace concentrations until something like and it is quite remarkably low sometimes in comparison to even the primary material which is alloying, which is that of carbon actually. So the other process which is important for me to discuss is heat treatment. So not only alloying, but supposing there is a pure phase or let us say an alloyed phase material which is there, let us say steel is a alloy of carbon and iron, right. So how can we achieve the properties of steel, material properties of steel, by not adding any other alloying element, but only trying to see the diffusion driven transport of the carbon with respect to the overall crystal structure of iron gets at a certain rate, equilibrated rate, and so that gives you a sense of what is going to be the overall hardness etc. of the structure. For example, let us say if I had austenite and if I wanted to heat it very rapidly by water quenching it and cold water, immediately you will get martensite state, which is known for its hardness. In fact, on the Rockwell hardness scale it reads about 65, and then it has more tensile strength like 175 into 10 to the power of 4 Newton per millimeter square, and it also reduces in area, percentage reduction is very low. Okay. Similarly, if you were to oil quench austenite, for example, you will have very fine perlite which also would have about 35 hardness, and it would have an ultimate yield stress of about 56 10 to the power of 4 and tensile stress of 112 10 to the power of 4. Okay. Or in fact, if you could just heat it by air cooling just directly, without just keeping it in normal room temperature after the heat treatment process, so that results in fine perlite. Why these different structures are produced is because you are not giving it enough equilibrating time in one case when you are rapidly cooling it vis-a-vis the case where you are slowly cooling it. So, the equilibrating time for the diffusion, the mechanically driven diffusion processes of carbon into the matrix happens at different rates, okay, owing to the different cooling rates. So, here for example it is a furnace cooled case where austenite converts into just coarse perlite. This is the slowest cooling process, okay. So, you are already keeping it into the furnace and allowing the material to cool with the furnace. So, that is the slowest cooling that you can say. So, that produces a different structure altogether, coarse perlite, which has a very low Rockwell hardness of about 15, you know. So, as opposed to martensite which was with rapid cooling, you can see the effect immediately coming through where a very low hardness is recorded only by changing the cooling rate, okay. So, that is why as I was earlier discussing, this 723 degrees Celsius temperature is very important, because beyond this the austenite steel is completely gamma iron, and then you know it just changes from that gamma into various states corresponding to the different cooling rates that are used, you know, at that particular point. So, it is thus obvious that by changing only the rate of cooling, different phases can be achieved, and so in order to address this issue, the cooling rates have to be demarcated in one page format, just like you saw the phase diagram, the equilibrium phase diagram. And so, these curves are known as the time temperature transformation curves or TTT curves, and I am going to illustrate to you how this TTT curve can be read and what actually is interpreted out of it. So, let us say the temperature is plotted, you know, in the vertical axis whereas the abscissa represents the time on a logarithmic scale. So, normally this right about here is what the TTT curves look like. Let me just blow it a little bit more, you know, and let us say magnify the curve a little more. So, here for example, as you can see, the transformation begins from this particular temperature, which is probably 723 degrees Celsius, and you know when let us say this is where the austenitic state is present. So, we call it austenite here, okay. So, it is gamma iron, you can say, with a FCC kind of you know structure where ferrite is present all through the gamma iron phase, okay. So, we start at theta 0 723 degrees, and let us say if we try to cool the iron at a certain rate which is given by this slope right about here. Mind you, this is a logarithmic time scale and this is the temperature. So, basically when I am saying the slope of this particular line as I am showing here, it is actually the cooling rate that we are referring to, you know. So, logarithmic sort of cooling rate that we are referring to. So, when austenite is brought to a temperature let us say theta 1 from theta 0 at an extremely high cooling rate, which can be considered almost equal to let us say 0 time, you know, because the rate is very high. So, you are changing from 723 to this let us say theta 1, which is just below 600 degrees Celsius here. At this point we are leaving, and then allowing the transformation process to take place. The transformation to perlite, as you can see here, begins after some point of time, you know. So, this much time, let us say this is T1, is spent in waiting, so that there is a mechanical diffusion which works out, and this phase right here which starts after this solid line here is the perlite phase, you know. So, this is let us say perlite. So, the perlite transformation happens to take place at or starts to take place from temperature T1, okay. So, you have to really wait by dropping down to theta 1 in almost no matter of time, and then wait for this T1 time for this the transformation to start taking place from perlite, you know. So, once this is done, this perlite transformation sort of completes up to the point B here, let us say this is time T2. So, the curve here for example in this particular zone actually represents the end of production of complete perlite. The region here is completely, you know, full of perlite. You may have coarse perlite or fine perlite towards the nose of the curve here, or at the bottom you have, you know, this sort of benite transformation. So, here for example in this particular case coming from T1 to T2, that means from point A to point B, you know, we can call this transformation an isothermal transformation. And one of the reasons why that is so is that you are doing this transformation all at the temperature theta 1 without changing it. So, this is called isothermal transformation. So, the transformations corresponding to the other temperatures theta 2 and theta 3, for example, if this allows to cool off beyond theta 1 are all shown here. For example, if it directly goes into a rapid cooling mode where the time spent in cooling is very low, you can see that here. So, it enters into this Martenside phase. Okay. So, this is Martenside. So, whatever I was showing there diagrammatically in terms of structures and cooling is being represented in this TTD curve as one snapshot. Now, you can change your rate of cooling and attain any structure that you would like for the engineering material to come up with. Okay. So, at about 500 degrees Celsius the transformation, as you can see here, starts after a minimum lapse of time. So, this area is therefore known as the nose of the curve, TTT curve, and it is a sort of you can say that the cooling rate is almost tangential. So, if the cooling rate were anywhere lower to the rate that the extremely high rate that has been shown here, there would be the production of a perlite phase which would actually come up here, okay, because then the rate would start and go through this whole perlite region before getting into martensitic state. But if you are having a rapid quenching like this where almost 0 time, then you just go tangentially to the nose and avoid getting into the perlite zone and go directly into the martenside zone. So, below the let us say 500 degrees Celsius temperature, the austenite would, supposing if I drop it somewhere here at theta 2, it would now isothermally convert into benite. It will not give you perlite anymore. Okay. So, beyond this particular thing you have benite, all this is benite, and it will not be able to get into the benite unless it crosses over the perlite zone which is here. So, austenite to perlite to finally benite if it is isothermally being transformed as a function of time. So, ultimately you get benite, but it comes through this zone right here. Okay. So, that is how you interpret from the time temperature transformation curve the various structures based on different time points. The other issue that I would like to discuss is only about the mechanical working and recrystallization, and as mentioned here the mechanical properties, example strength and hardness of a polycrystalline material are governed by grain size of the material. Okay. You had earlier looked into the dislocation theory where we assume that if there is a jamming of the dislocation across the grain boundaries while traveling, there is going to be an increase in the strain hardness. I mean the strain hardening processes would try to take place, overall hardness would change because of that, will increase because of that. So, here the strength and hardness of a polycrystalline material are really a function of the grain size. So, meaning thereby if I wanted to do mechanical working on the material, for example, let us say we have shown 3 cases here where mechanical working is being done. This is a case of forging. Okay. So, circular grains otherwise are converted into elliptical here. A case of rolling where there is a circular grain being converted into elliptical, as you can see by a roll pressure, or machining where the circular grain again are being converted into elliptical by means of the tools, etc. So, here during the grain deformation processes there are going to be various mechanically structured grains which are going to be formulated, and obviously if the grain structure changes because of the deformation, there is going to be a change in the overall ductility or strength properties, okay, of the material. So, you can look at it that tensile strength, if we plot as a function of average grain diameter, the increase in the grain diameter, the ductility would increase and the strength would reduce. Okay. So, the other aspect here is that mechanical working can be followed by a recrystallization where there is again a fresh grain growth, because you are now taking it above 723 degrees Celsius to the gamma austenitic phase and again bringing it down. Okay. So, even that recrystallization process can be initiated with mechanical working, so that you can have a control on the overall grain size which would determine your ductility or strength properties. So, in a nutshell then we have looked into the various aspects of how you alloy the materials to control the strength. We have also looked into the various aspects of how you heat treat to control the strength, and then how you are able to read from a single snapshot how the strength is going to change or how the structure is going to change based on different rates of cooling. Okay. And then finally you have also looked into the mechanical working and recrystallization processes. So the figure on the right shows the grains are deformed by various mechanical working processes. We can easily see that the effective grain size is reduced because the surface area of each grain increases, whereas the volume remains the same. It is possible to restore the original grain geometry by heating the material up to the temperature where the new fine grains are formulated, and that process is known as recrystallization. Okay. The temperature needed to achieve this is known as the recrystallization temperature, and if the material is kept for a considerable period of time at this temperature, the newly formed fine grains would grow in size and again formulate the similar original property of the material. On the other hand, if the material is cooled quickly, the grain size remains small, and it should be noted that in mechanical working processes the grains are deformed, whereas in recrystallization new grains are formed and their sizes can be controlled. Okay. So you can play around with the way that you cool after recrystallization, and even before recrystallization do mechanical working to reduce the grain size to a desirable level. Okay. And that really determines your mechanical properties. With that, I would like to close on this module. In the next module we will start understanding the casting process in great details, because I think we have now enough understanding about material properties for us to be able to go into the modeling and design of casting. So with that, I would like to close this module. Thank you.